So, the chapter 17 homework is due on Friday. The chapter 17 quiz will be on Wednesday. In SI, please turn in the leather lab if you haven't. And there will be a lab today. Which I need to go print out, but so Saturn has 274 known moons. The textbook is out of date. It says there are 82. This is because part of this is because like it was out of date a while ago, but they just added like 120 not very long ago, like in March. The largest of these is Titan. Titan is interesting because it's, other than Earth, pretty much the only place we know that has it has a thick atmosphere and it has liquid on its surface. So it's got something like a hydrological cycle, except it's not with water, it's with liquid methane and other hydrocarbons. So it's the only moon in the solar system that has a dense atmosphere. Atmosphere is primarily nitrogen, about 90% nitrogen with argon and methane. This probably makes it pretty similar to Earth's early atmosphere. So also studying the chemistry in the atmosphere of Titan is interesting. And Titan's surface includes lakes of liquid methane. So here is a video showing the surface of Titan and the various lakes of methane on the surface, imaged with radar. I just realized I may not have the right sound setting. Just make sure. Yeah, I have the sound settings. But I think this might not actually have any audio. Yeah. So, flying over the various hydrocarbon seas and lakes, sometimes in Titan. The only other place in the solar system with stable liquid. This is the largest of the Titan seas, it's back in May. One of the more interesting things we found about moons of Saturn is that there is Enceladus, which is a pretty small moon. It's only a few hundred miles across. But it has indications of having a liquid water ocean that's in contact with the surface, because it's shooting out these fountains of ice particles that have been detected. So there's active geology and a liquid ocean. That's the kind of situation where it's interesting, complicated chemistry like what creates life could happen. So it's one of those potentially interesting places. And here is a video about water on Enceladus.
Recently, Cassini has found that a tiny moon that orbits around Saturn has jets and plumes of water coming out of it. These particles go out and they form the E-ring. And in flying through the E-ring, one of the instruments on Cassini, the Cosmic Dust Analyzer, can take those particles and get a composition. And as part of that, they see salt.
This is salt, and this is what we found in the ice particles we detected in Saturn's E-ring. And what we think is that the salt comes from an ocean below the surface of the moon Enceladus. The sodium is a tracer for a subsurface ocean. That's the material of the ice particles, a kind of water, like on Earth.
And that salty ocean tells us something about what might be going on inside of Enceladus to create the jets and plumes that you need. Water, liquid water, in contact with the rocky core to get out the sodium. You could sort of think of maybe the plumes of maybe sort of the breath of Enceladus, coming out and telling us something about its interior.
So what we can say is we have a reservoir of liquid water, and liquid water is one of the preconditions for forming life.
I was surprised and also very excited to find out that, we're getting closer and closer to the conclusion that you have liquid water, possibly a liquid ocean, on a moon that's so tiny, and in a place where we didn't expect to find conditions where you might find life. This tiny moon, just 300 miles across, that might have liquid water and the conditions, the precursors for life. The focus, as Cassini continues in its Equinox mission and continues on into the future, will be to have more close flybys of Enceladus, to fly through that plume, fly close to this tiny moon to learn more about the processes going on inside.
Okay. So moons and rings are interconnected. They interact. Without moons, the rings wouldn't exist. Moons create the structure in the rings. They help keep them stable. They also probably provide the material for the rings. So moons keep rings confined. One of the ways this happens is with shepherd satellites, like the two small moons shown here. The gravity of these moons pulls this ring tighter together. They keep the ring particles in place. The rings would dissipate over astronomical timescales if they aren't resupplied. So it's thought generally that they're resupplied by new particles from impacts on moons. So material from moons feeds into new material for the rings. So here are some shepherd moons on Saturn's F ring. You can see how gravity from these moons is pulling the ring tighter together. You can see the actual waves of gravitational compression passing up here. Let's move on to Uranus. So the large moons of Uranus are Miranda. These are the larger moons of Uranus. They're generally classified as medium moons. Miranda has an orbital period of 1.41 days. It's about 130,000 kilometers from Uranus. It's got a diameter of 480 kilometers and a density of 111 kilograms per million. So Miranda, then Ariel. So these are going from smallest to biggest. Miranda, then Ariel, then Umbriel, then the two biggest are Titania and Oberon. Uranus has 29 known moons. The textbook's out of date. It says 27. And the biggest of the moons, Oberon and Titania, they're only 1,500 or so kilometers across, less than 1,000 miles. So Miranda is kind of unique because its structure is very rugged. Like Miranda it's covered in these bizarre geologic forms where it was like something happened that basically tore it apart, and the whole thing was, then got recompressed. Neptune has 16 known moons. The largest of these, Triton, is unique because it orbits in a retrograde manner. Triton, the largest moon of Titan, basically orbits backwards. Almost everything in the solar system both rotates and orbits in the same direction. Counterclockwise if you look at it from, above the North Pole. Triton goes the other way around Neptune. Neptune is orbiting counterclockwise. Triton is orbiting the opposite. Neptune is rotating counterclockwise. Triton is orbiting backwards. Almost all the other moons of Neptune also go in a normal direction. Triton is just backwards. So the thought is that Triton is some sort of captured object that maybe ran into another moon or something, slowed down enough to get captured by Neptune and end up orbiting. There's a lot of debate about how it could have slowed down enough, because the thought is that anything with enough energy, with an impact with enough force to slow it down could have also destroyed it. Come on. Oh, yes, 17 continue. That's what I need to do. So here's a video about what's up with Neptune's moon orbiting backwards.
(1989). After a 12-year journey, NASA's Voyager 2 mission reaches the outer solar system and the gas giant Neptune.
First seeing the images of Neptune was really exciting, because we went there with no idea what we were going to find, and suddenly here are these high-resolution images.
It's a triumph for Voyager 2. But when NASA examines Triton, the largest of Neptune's 13 moons, they spot something disturbing. The moon is going the wrong way around the planet.
When you look at the Earth-Moon system, the moon's going around the Earth just like this, kind of close to the equator of the Earth. When we look at Triton, what we see is the moon's going around in the other direction. It's the only large moon of any of the planets that does this.
Triton's behavior seems completely unnatural. It contradicts everything we think we know about how planets and moons form.
Most moons get created as the planet itself gets created. So you have this swirling ball of gas and materials that are collapsing down into the central planet, and then some debris left over collapses down into the satellite. So you expect all the objects to go in the same direction around the planet. That's very understandable. What's not understandable is how do you get a moon, especially a large one, to go in the opposite direction.
The resemblance to the planet-destroying artificial moons of the Star Wars movies is striking.
As they're approaching the Death Star, Obi-Wan peers through the windshield and says, "That's no moon."
If you want to park in the solar system, keep an eye on Earth and all the interesting things going on there, Neptune's the perfect place to park your artificial planet.
Triton's surface seems to support the theory. It appears to have areas that are smooth as metal, reflecting 70% of the sun's rays.
Triton's a very confusing world. the orbit and its the type of a moon it is, yeah, Triton is very confusing.
Even for the most skeptical scientist, all the evidence suggests that Triton is no ordinary moon.
It's extremely unlikely that Triton formed orbiting around Neptune. It doesn't make any sense for it to have formed locally.
There is one obvious problem with the Death Star theory.
If I'm flying an artificial planet through space and I decide that I want to park it on Neptune, I'm going to be sure to go the right way around the planet if I'm trying to hide.
Triton is not a Death Star. It's not made out of materials we'd expect it to be made out of if somebody was building a thing. It's made out of natural materials that we expect.
But if Triton is not artificial, why is its surface smooth?
On Triton, we saw eruptions of material into its thin atmosphere. Watery eruptions can freeze and make a smooth surface, at least filling in the impact craters.
People call it cryovolcanism, an ice-based, cold, volcanic process.
That still leaves the mystery of Triton's weird orbit. But astronomer Dr. Craig Agnor has a theory.
Because Triton is going in the opposite orbital direction of all of its neighbors, the general idea for its origin is that it made a close approach to Neptune, and it somehow became a bound companion.
Triton came from somewhere else, flying through space until it hit something near Neptune and was captured by the planet's gravity. But even this extraordinary idea only partially solves the mystery.
If the object that Triton collided with was large enough to slow it down and enable its capture, it was also likely large enough to destroy it.
To date, no one has explained how or why Triton survived its hypothetical collision.
Now, not only, moons exist around objects other than major planets. So, for example, the dwarf planet Pluto has 5 known moons. These are Charon, Styx, Nix, Kerberos, and Hydra. The largest of these, Charon, was discovered in 1978. It's about half the size of Pluto. They're tidally locked to each other. Some people argue that, in fact, we should consider Pluto and Charon like a binary dwarf planet because Charon's so big. It's the largest satellite in relation to its parent planet. Charon and Pluto always, the same side of Charon and Pluto always face each other. So they're synchronous because of that. And then there are 4 smaller moons. Styx, Nix, Kerberos, and Hydra. And, things with moons aren't uncommon. So this is a video a reminder about what happened with Pluto and how...
You may have noticed that we now have only 8 planets in our solar system. Most of us grew up with 9. Pluto was the 9th, but it's no longer a planet. I'll explain why not, and also, if Pluto is no longer a planet, just what is it? Pluto was discovered back in 1930 and added to the list of planets. Its orbit is a strange one, taking it for a time closer to the Sun than Neptune. But more of its time is spent beyond Neptune, all by itself. At least we thought it was by itself. In the early 1990s, 2 smaller objects were found in orbits near Pluto's, in what is now called the Kuiper Belt. These discoveries were followed by more objects in the Kuiper Belt, all smaller in dimensions and less massive than Pluto. But even then, some astronomers questioned if Pluto should be considered just another Kuiper Belt object instead of a planet. And this wasn't the first time something like this had happened. In 1801, a new object was discovered orbiting between Mars and Jupiter. It was given the name Ceres. During the early 1800s, Ceres, along with its neighbors Pallas, Juno, and Vesta, were considered planets. But that changed with the discovery after 1845 of many more of what are now called asteroids, also orbiting between Mars and Jupiter. After that, Ceres and the rest were reclassified from planets to asteroids in what is now called the asteroid belt. So it was natural that many would question whether Pluto should still be called a planet, given that many more objects were found around its orbit. Pluto's status as a planet was then put under even more pressure in January 2005 when Eris was discovered in the Kuiper belt. Eris is practically the same diameter as Pluto, but its mass is around 25% more due to its higher density. The discovery of this more massive object alongside Pluto meant that either Eris should be added to the list of planets, or Pluto should be reclassified to something else. In 2006, the International Astronomical Union, the IAU, convened to decide just what the definition of a planet should be. The final decision was that a planet should meet 3 criteria. 1. The planet is in orbit around the Sun. Check. Pluto orbits the Sun. 2. The planet has sufficient mass for its own gravity to pull it into a nearly round shape. Check. Pluto's gravity has made it nearly round. And 3. The planet has cleared the neighborhood around its orbit. This is done either through collisions or redirecting objects away. And this is where Pluto fails. Pluto accounts for only a small fraction of the mass around its orbit. To put this into perspective, there are thousands of relatively small asteroids, called near-Earth objects, around Earth's orbit. But the Earth's mass is 1.7 million times the rest of the mass in its orbit. On the other hand, you'd need around 14 Plutos to equal the mass of everything else in its orbit. So if Pluto isn't a planet anymore, what is it? At the same meeting of the IAU, a new classification was formalized, called a dwarf planet. What's a dwarf planet? A dwarf planet is one that meets the same first 2 criteria for a planet, but has not cleared the neighborhood around its orbit, just as Pluto hasn't. Plus a 4th criteria. A dwarf planet is not a satellite, like our moon is a satellite of the Earth. Check. Pluto isn't a satellite of any other object, other than the Sun, that is. So Pluto is a dwarf planet, and so are Ceres and Eris. As of now, there are only a handful of dwarf planets, but it's suspected that there may be up to 200 in the Kuiper belt, and maybe even more than 10,000 when objects outside the belt are considered. This video was made as a collaboration with All Time Numbers. Check out this stunningly awesome video of theirs, The Universe in Numbers, by clicking on this preview or on their logo to go to their channel.
Discover the universe in numbers. The diameter of the observable universe.
So this is an image of Charon, and here is an image of the 2 Pluto and Charon orbiting each other, and you can see they're orbiting around their mutual center of gravity here. So this is Charon, is imaged by, I believe, New Horizons. So this is Charon and Pluto orbiting each other. You can see they have the same sides always facing each other, and they're orbiting around their mutual center of gravity, which is slightly outside of Pluto. And here's a video showing the orbits of the chaotic orbits of all of Pluto's moons. So here's Pluto and Charon orbiting each other, and here are the other moons of Pluto tumbling around. And you can see how they get kicked by Charon, and that changes their motion. So other dwarf planets have moons as well. Ceres has no moons. There is an asteroid that has a moon, but it's not actually a dwarf planet. It's small. Eris has 1 known moon, Dysnomia, which little is known. Haumea has 2 known moons, Iaika, I probably mispronounced that, and Namaka, and they show the signature of water ice. Makemake has a single discovered moon that I don't know if it has a name. Just look it up. Okay, no, it doesn't have a special name. It's called MK2. Other potential dwarf planets are known to have moons as well. Gong has one known moon, Dianglu, discovered because of how it showed Gong's rotation. Slowed Gong's rotation, sorry. Quaoar has one known moon, Weiwat. Orcus has one known moon, Venth. And Salacia has one known moon, Ectea. So lots of the dwarf planets have moons. So now let's move on to talk about smaller solar system bodies. We talked about moons, we talked about dwarf planets. Let's talk about the little things that are sort of everything else. So asteroids, meteoroids, meteors, and meteorites, and comets and interplanetary dust. So asteroids are space rocks that are rocky, primarily made of rock and metal. They're primarily concentrated in the asteroid belt between Jupiter and Mars. There are over 20,000 named or numbered objects that orbit the sun in a belt between Mars and Jupiter. This contains millions of asteroids, but there are asteroids that are close. There are a few asteroids that are even so close to the sun as to be entirely within the orbit of Venus. There are asteroids that pass through Earth's orbit, and there are asteroids further out. About 100,000 are bright enough to be photographed by Earth-based telescopes, and they're sometimes referred to as minor planets. Minor planets are anything that's not big enough to be a dwarf planet that's orbiting the sun. So basically, asteroids are rocky, comets are icy. That's sort of the difference. Sometimes there's a little fuzziness about what we should call a comet, but that's the sort of general difference. So here is where most of the asteroids are in the asteroid belt. They're mostly between Mars and Jupiter. They're patterned. This area was prevented from forming a planet by the gravity of Jupiter. You can see patterns in the asteroid belt tied to the orbit of Jupiter. It's affected strongly by the orbit of Jupiter. It's sometimes attributed to the breakup of a former planet. This is not the case. There's not enough stuff there to form a planet. The estimates of the total mass of the asteroids is much less than the mass of an ordinary planet. A more plausible explanation is that this is debris that was never allowed to form a planet because of the gravitational force of Jupiter. This is backed up by the fact that there are patterns in the asteroid belt that are resonances to Jupiter's orbit. Jupiter is keeping the asteroid belt in this dispersed state. Small space rocks are called meteors. But they're called meteoroids when they're out in space. So interplanetary metallic and stony objects that range from about sub-millimeter to hundreds of meters across, little space rocks, we call them meteoroids. When a meteoroid hits the Earth's atmosphere, it heats up. It gets really hot and makes a bright streak of light in the sky. That is a meteor. If that meteoroid manages to survive to the surface, which most don't, what remains on the surface is a meteorite. So that's the difference between meteors, meteoroids, and meteorites. Basically where they are. In space, it's a meteoroid. While it's falling through the atmosphere, it's a meteor. Once it's on the ground, it's a meteorite. Like all the other geological terms. back to now. Yes. Okay. So here's a short video about that.
In 1969, a celestial light show burst through the sky over Chihuahua, Mexico. These lights in the sky are called meteors. Or is it meteorites? Maybe meteoroids? Are those all different things? And if they are, what is the difference? Actually, they are all different, but they're pretty closely related. The streaks of light are in fact meteors. But the small rocky bodies that cause the lights, those are meteoroids. And when a piece of a meteoroid survives the trip and hits the ground, that object is called a meteorite. So let's talk about our Mexican light show. It actually started out as a single object about the size of a car flying through space. That object was a meteoroid, a body orbiting the sun that's smaller than an asteroid or comet. In February 1969, that meteoroid hit Earth's atmosphere and it hit it fast. Meteoroids fall at a minimum speed of 25,000 miles per hour. At that speed, the friction from the air began to heat up the object. In fact, it made it so hot that it began to burn brightly across the sky as a meteor. This particular meteoroid didn't just burn, it exploded into pieces. Now, most meteoroids burn up entirely as meteors, and some of these pieces did just that. But a few made their way through the atmosphere to hit the ground. Those remnants are known today as the Allende meteorite. Yeah, even though there are lots of stones, they're all considered part of the same meteorite. All in all, about 2 tons of this meteorite was recovered. Study of the Allende meteorite reveals that it is one of the oldest objects in the solar system, older than Earth itself. So where do meteoroids like this come from? Well, almost all of them are actually fragments of asteroids, the larger rocky bodies that orbit the Sun in a big belt between Mars and Jupiter. A few, though, are actually moon rocks, and some even come from Mars. So if you ever see one of these interplanetary travelers lighting up the night sky, now you'll know that you're seeing a meteor caused by a burning meteoroid. And if you're very lucky, you might even find a meteorite when it hits the ground.
So, when a large meteorite it hits the ground, you get things, impact craters. So, one of the best preserved is the Barringer meteor crater in Arizona. It's usually just called the meteor crater, not meteorite crater. But which is a large crater in Arizona. The estimate is that the impact was estimated to have occurred about 50,000 years ago when a large meteorite struck near Winslow, Arizona. Very big crater. It was a big rock. Would have caused, killed a lot of stuff around it when it hit as well. Not a huge area, but big hot impact. Would not have killed any humans because humans had not made it to North America by that point. About 50,000 years ago. So humans didn't get to the Americas until like 20, 30,000 years ago at the earliest. And those are the early estimates. There's a lot of debate about when exactly, but this is well before even the earliest estimates. So they're just warned humans on the continent. Yeah. But it killed a bunch of animals. So, comets are relatively small objects. I mean, they're asteroids. They're the same size as asteroids, roughly. But they're mostly made of dust and ice. They're what you get out further, generally further from the sun, where you get a lot more ice instead of rock. So comets and meteors and asteroids are very interesting to study because in general they're sort of leftovers from the formation of the solar system. So they tell us a lot about the early stages of the solar system. Now comets get dramatic because they're balls of ice. So if they have an elliptical orbit where they'll get close to the sun, when they get close to the sun, they heat up. And basically the outer layers boil off. They cook off the outer layers and they start spewing out gas and dust. And that gas and dust gets pushed away by the solar wind and the light of the sun and creates a dramatic tail. So the tails of comets don't trail behind them. They always point away from the sun. So here's a short video about comets.
Comets are created in the deepest reaches of the solar system. They travel in giant, elongated orbits far away unless some force knocks them out of their orbit towards the sun. When a comet approaches the sun, its ices and gases called volatiles vaporize to produce the tail in a process called sublimation. Although a comet is mostly ice and dirt, its surface is a shell of carbon that forms as the volatiles below the surface collect on it during the sublimation process.
It's a bit like a baked Alaska, where you take a brick of ice cream and you cover it with meringue, throw it in the oven, and the outside layer protects the inside layer from the warming influence of the sun, so it's a very complex structure.
Asteroids are other rocky bodies that also orbit the sun, but have few, if any, volatiles. They orbit either in a band of asteroidal debris called the asteroid belt, or in another, more distant band of debris called the Kuiper belt.
If you see an object and it happens to have a tail, maybe from sublimating gases or something, then they call it a comet. An asteroid is something without a tail. And that's the only distinction that observers would use.
Originally, it seemed to everyone to be clear. Asteroids were these lumpy rocks, mostly between Mars and Jupiter, but sometimes you find them elsewhere. And comets were these things that came from further out, and when they got near the sun, they'd warm up and volatiles would start to give off gases and they'd have a tail. So comets had tails and asteroids didn't.
Blurring the line between comets and asteroids even further, and contrary to popular belief, the phenomenon on Earth known as a meteor shower is primarily attributed to comets and not asteroids. A meteor is the visual display of light in the sky as a bit of dust and dirt burns up upon entering our atmosphere.
There's the dust material that comes off from a comet that makes the tail that we see in the sky for a bright comet. If that material intersects the Earth's orbit, particularly at night, then we would see meteors coming from those bodies as they hit the atmosphere and were vaporized at the top of the atmosphere.
Right now, there are about 30 to 40,000 tons of asteroid and comet material that land on the Earth every year.
That's a lot of dust burning up in the sky and settling to Earth. But it's not just comet dust that can hit the Earth. Whole comets can. Geologic evidence suggests large bodies, possibly comets, have already plowed into our planet, destroying many of Earth's creatures.
So yeah, there's some debate about terminology for asteroids and comets. A lot of the time, people just call the icy bodies further out in the solar system, the ones that are beyond Neptune, just trans-Neptunian objects. You just not have that debate. But a comet, so things that make tails are definitely comets, and they have ice and volatiles that cook off. So a comet generally consists of 4 parts. There's a nucleus. This is the kind that you're seeing as a dramatic comet. There's a nucleus that's typically a few kilometers in diameter, and it's composed of rocky or metallic material surrounded by ices and other volatiles. There's the coma, the head that surrounds the nucleus. This is several hundred kilometers in diameter, and it's material cooking off of the nucleus as it approaches about 5 astronomical units of the sun. Then there's this tail, which is a long tail composed of ionized molecules, dust, or a combination, and it can be millions of kilometers in length. This is material being pushed away from the comet by both the dust is generally pushed by the actual light of the sun, and the ionized gases are being pushed away by the solar wind produced by the sun. The tail can be long and voluminous. It's composed of ionized molecules, dust, or a combination. It can be millions of kilometers in length. And then there's a cloud of hydrogen from mostly, a lot of these volatiles are hydrogen compounds. They're things like water. And water is H2O. And it turns out the light from the sun can break them down, and you get actual just, yeah, the water molecules get broken apart by radiation from the sun, and you get a cloud of hydrogen around the coma. So here are the principal parts of a comet. There's the nucleus, sort of the rocky lump in the center. The coma around it, the glowing ball. There's a big hydrogen cloud around that. And then there's 2 tails. There's a dust tail and an ion tail. And then under certain circumstances, those 2 can separate because they move at different speeds. So they get bent different amounts by the fact the comet is traveling around the sun and the tails are being pushed away from it. So the dust trail gets bent more than the ion trail. So here you can see images of a comet as it gets close to the sun and gets a tail. You'll notice the tail is always pointed away from the sun. It's not trailing behind the comet. That only happened sort of at the very beginning. It's pointed away from the sun. It does not indicate the comet's direction of movement, which is why whenever they animate comets or draw comets and things, they're always wrong. The tails are always trailing behind the moving comet, which is not at all what's happening. So that is the end of chapter 17. So natural satellites are referred to as moons. Our moons is the largest in size of any moon orbiting the terrestrial planets. We only see one side of the moon since its period of rotation on its axis and its period of revolution around the Earth occur at the same rate. The gravity of the moon is only 1/6 of that of Earth. Radioactive dating has shown that the moon's age is less than that of the Earth. Currently, the moon does not possess a magnetic field. Bowl-shaped depressions on the moon's surface are referred to as craters. The light-colored surfaces of the moon are referred to as the highlands. The dark areas of the moon are referred to as maria. These dark areas are theorized to be the result of ancient volcanic activity on the moon. The streaks reaching outwards from some moon craters are called rays. Long trenches on the moon are called rills, I think. The moon's orbit is tilted 5 degrees with respect to the Earth's orbital plate. It takes the moon about 1 month to revolve around the Earth. The phase of the moon when the moon can't be seen is called the new moon. The phase of the moon when the full disk of the moon can be observed is called the full moon. If the moon is getting larger, we say it is waxing. If it's getting smaller, we say it is waning. If less than half of the moon is visible, we say it is a crescent moon. If more than half of the moon is visible, we say it is a gibbous moon. When the moon is between the sun and the earth, a solar eclipse may occur. When the earth is between the sun and the moon, a lunar eclipse may occur. The darkest shadow region during an eclipse is called the umbra. The somewhat dark region during an eclipse is called the penumbra. Tides are greatest on Earth when the sun and the moon are in line with the Earth. 2 high tides and 2 low tides occur each day on Earth. When the Earth, moon, and sun are in line, we get spring tides, particularly large tides. When the moon is at first and last quarter, we get neap tides, smaller tides. The 2 terrestrial planets that have no moons are Mercury and Venus. The Jovian planet with the most moons is Saturn. The moon of Jupiter that has active volcanoes is Io, which planet has the largest moon in the solar system is Ganymede orbiting Jupiter. So that moon is named Ganymede. The moon Titan, what the moon Titan has that's unique for a moon is a thick atmosphere and stable liquid on the surface. The planet that has a moon that revolves in a retrograde orbit is Neptune, and the moon is Triton. Pluto is classified as a dwarf planet. The collection of small bodies between the orbits of Mars and Jupiter are called the asteroid belt, or asteroids. Well, that is the asteroid belt. A meteoroid that reaches Earth's atmosphere and glows brightly as it burns up is called a meteor. A meteoroid that reaches Earth's surface is called a meteorite. Comets usually have a very elliptically shaped orbit. When they get close to the sun, they heat up, creating the tail and glowing. The rocky portion of a comet is called the nucleus. The glowing part of a comet that forms as it approaches the sun is called the coma. The rear portion of the comet that's composed of ionized material and dust is called the tail. The portion surrounding the dust of the coma is thought to be a cloud of hydrogen gas. The tail of the comet is pointed away from the sun as it approaches. So that was the end of chapter 17. Let's get a little ahead on chapter 18, where we talk about the universe as a whole. So just a reminder, we have a lab today. Your quiz on chapter 17 will be on Wednesday. Your homework on chapter 17 is due on Friday. And I'm going to start off on chapter 18 so we don't end up getting behind. So when we talk about the universe, we're talking about the totality of all matter, energy, and space. So in this chapter, we're going to talk about stars, galaxies, and cosmology. We're going to discuss our sun and the classification of the stars, galaxies, which are big assemblages of stars, and cosmology is the structure and evolution of the universe. So the way we study the universe is primarily through light. Stars and galaxies will emit the full spectrum of electromagnetic radiation. For many years, we were only able to gather information from one type of electromagnetic radiation, visible light. But in 1931, that's when we started having radio telescopes that became operational, giving scientists the ability to gather information at other wavelengths. And now that we started to put telescopes in orbit, we can gather a number of wavelengths we weren't able to before, because many of those wavelengths get blocked by the atmosphere. So the Earth's atmosphere absorbs many of the incoming non-visible wavelengths of light. So that's unfortunate for astronomers. So we've devised ways to minimize or eliminate Earth's atmospheric filtering. We put observatories on high mountains where the atmosphere is thin, and we use balloons, aircraft, and eventually satellites and spacecraft to transport instruments to even greater heights. So our best telescopes are now in space, orbiting the Earth, avoiding the issues caused by the atmosphere. So let's talk about the difference between astronomy and astrology. They used to be the same thing in many ways. But over time, we developed when astronomy is the actual scientific study of the universe beyond the atmosphere of Earth. We study the electromagnetic, largely astronomers study the electromagnetic radiation emitted by celestial bodies that eventually reaches their instruments. It used to be exclusively, but now we have a few things that can detect other things. Astrology is a pseudoscience that uses scientific sounding terminology to make up stuff about how one's birth, the position of planets and stars at the time of your birth, can affect an individual's personality and or future. It doesn't actually make any real testable predictions, or if it does, they tend to not be right. Now, many people closely follow their astrological chart. There's no known scientific basis for a cause-effect relationship. And you can do studies to show there's no real basis for cause and effect. The secret to being good at astrology is to make statements that are vague enough that they are always true. And basically prey on certain human mental biases. The celestials, when we talk about how we think about where everything is located in space, we can use something called the celestial sphere. This is like making a map of the sky. What we do is we basically create an imaginary sphere of the sky on which all the stars seem to be located. And during any given night, this great dome of stars appears to progressively move westward from an observer's vantage point on Earth. And we can define the location of stars based on basically a latitude and longitude on the celestial sphere. There's a few important points. There's the north celestial pole, which is the point in the northern hemisphere that the stars seem to rotate around. The north celestial pole currently coincides with the star Polaris. But that was not always the case, and it will not always be the case. There's also the south celestial point, which is the point in the southern hemisphere the stars appear to orbit around. There is no particular star at the south celestial. The north celestial pole and the south celestial pole are simply extensions of the Earth's rotational axis. And the star's apparent movement around these poles is really just due to the Earth's actual rotation. The stars aren't moving, we are spinning. So there's some important locations of the celestial sphere. These include the ecliptic, the celestial equator, and the celestial pole, the north celestial pole and the south celestial pole. The celestial equator is much like the Earth's equator. It's just an extension of the Earth's equator. The point in between the celestial poles above the Earth's equator. The ecliptic, on the other hand, is the apparent path of the sun across the stars. The apparent annual path of the sun on the celestial sphere. And the ecliptic, because the Earth is tilted compared to its orbit, so the ecliptic is basically Earth's orbit around the sun, how it slices across the sky. So this is due to Earth's orbit around the sun and not because of the sun's actual movement. But because the Earth is tilted with respect to Earth's orbit, the ecliptic is not aligned with the celestial equator. So if you look at the celestial sphere, there's the celestial equator, the north celestial pole, the south celestial pole, and the ecliptic is at an angle. It's at 23.5 degrees. And that's the path that the sun takes across the sky. And they intersect at 2 points. Those 2 points are the vernal equinox and the autumnal equinox, the 2 equinoxes. So the 2 points where the ecliptic and the celestial equator intersect are called the equinoxes. So as the sun appears to be moving southward on the ecliptic, it intersects the celestial equator around September 23rd at a point called the autumnal equinox. And about 6 months later, it appears to be moving northward on the ecliptic, and it intersects the celestial equator around March 21st at a point called the vernal equinox. And the traditional zero we use for measuring locations of stars. So north and south, much like latitude and longitude on Earth, north and south have a natural zero, the equator. But east and west don't. We need to choose an arbitrary location. For the celestial sphere, there is actually a nice location. We can use one of the equinoxes, that intersection point of the ecliptic. And the traditionally used one is the vernal equinox. So on these 2 days, the vernal equinox and the autumnal equinox, the sun is located directly over the equator. In every location on Earth receives an equal amount of daylight and darkness. So generally angles on the celestial sphere to measure locations. The 0 point is the vernal equinox. We go up and down for, ascension, basically, or just latitude and then around. So the 2 solstices also mark significant points on the solar ecliptic. The summer solstice is the point where the sun's location is the furthest north. The winter solstice is the point where the sun's location is the furthest south. The celestial prime meridian, which is our 0 point for measuring around the celestial sphere, east and west, basically, is the half circle created by the intersection of the north celestial pole, the vernal equinox, and the south celestial pole. So the celestial prime meridian is therefore used as a reference line or a starting line to measure celestial longitude. And basically you go around, you measure right ascension and what's called declination. The right ascension is like longitude, declination is like latitude. So the measure of celestial longitude is called right ascension of the star or galaxy. The right ascension is the position of the star or galaxy to the east of the celestial prime meridian. It gets measured in hours, with the full circle having a total of 24 hours. I think it sometimes also gets measured in degrees, but hours is a traditional way to measure it. And the declination of the star galaxy is angular measurement in degrees, north or south of the celestial equator. And these are just, an agreed on system for where we're going to talk about where things are located in the sky. Maximum right ascension is 24 hours, and maximum declination would be either plus 90 or minus 90 degrees. So that covers, left, right, up and down in the sky, but we haven't talked about how far away things are. So when we talk about the distance to various objects, using meters or just regular distance units is inconvenient because they're way far away. So we use different units that reference things that we can measure relatively easily. So the distances for all the objects in the solar system are all measured in astronomical units, which is the mean distance between the Earth and the Sun, which is 1.5 times 10 to the 8th kilometers, 150 million kilometers. And part of this is actually because for the longest time, we knew all the relative distances of all the objects in the solar system, but we didn't actually know exactly how far those distances were. We didn't have a good measure of the distance from the Earth to the Sun or any fixed distance. We could measure everything in relation to the Earth's orbit, but we couldn't get how far away things were. Then, for further objects, for stars, there are 2 sets of units. There's 2 units that get used commonly. One is sort of a reference based on the speed of light, which is a large distance, but it's a nice intuitive thing to work with. It also is very helpful due to the fact that light takes time to travel. So whenever you're seeing something, you're seeing it in the past, which is important in astronomy because as we look further and further into the past, the things we're looking at are older and older. So a light year is the distance light travels through a vacuum in 1 year. That is 9.5 times 10 to the 12 kilometers. Or 9.5 trillion kilometers. Yes, that's right. So that's a nice natural unit to measure distances. It's a light year, the time it takes for light to travel a year. The nearest star to us is 4 light years away. And then you can have millions of light years and so on. Up to billions, because the universe is only about 13 billion years old, 14 billion years old. It's about 13.8 there. A parsec is another distance unit. And this is based off one of the methods we use for measuring the distance to nearby stars. So one of the ways that you can measure the distance to nearby stars is parallel, because the Earth orbits around the sun. As the Earth orbits around the sun, the positions of stars will change in the sky. And this is what's known as parallax. You can see this yourself if you hold out a finger and look at it, and then look at it with one eye and switch to the other eye. You'll see it moves against the background of what's around you. And you can use the size of this parallax, the size of this shift, to measure distance. But stars are very far away, so their parallax is small. And in fact, so there's a unit based on the distance to a star when it exhibits a parallax of 1 second of arc. 1 second of arc is, there's 60 minutes in a degree, and then there's 60 seconds in a minute. The 1 second of arc is 1/3600th of a degree of, around across the sky. And that is a distance of 1 parsec. You may have heard the term parsec before, which is about 3.26 light years. And the nearest star to us is more than 1 parsec away. So all parallax we observe is less than 1 arc second in size, which is why it wasn't observed, which is one of the things that was used as an argument against heliocentrism, the fact that it wasn't observed. But yeah, that's parsecs. So parsecs are the other common unit used. So 1 parsec is about 3.26 light years. So as you go from July to January, you can see a nearby star will change its position on the other side. The closer the star, the bigger the shift. And if you take that angle in arc seconds, 1 over that is the distance in parsecs. So as a viewer's position changes throughout the year, the position of a nearby star will appear to shift relative to more distant stars. This apparent annual motion of the star is called parallax. The closer the star, the greater the shift. And to calculate it, Proximus is just 1 over the parallax. It gives you the distance in parsecs. The annual parallax of Proxima Centauri is 0.762 arc seconds. To calculate how far Proxima Centauri is from us, we just do 1 over 0.762 arc seconds, and we get a distance of 1.31 parsecs. This method of measuring distance only works for the nearest stars. Eventually, that parallax is just too small for us to see. But then we move on to other ways of measuring distance. Sirius is the brightest star in the night sky. The annual parallax of Sirius is about 0.376 arc seconds. So to find the distance, the distance is 1 over parallax. So d equals 1 over 0.376 arc seconds, which gives us 2.66 parsecs. And parallax cannot be observed with the unaided eye. The first person to observe stellar parallax was Friedrich Bessel in 1838, German astronomers, because even for the smallest stars, parallax is very small. The parallax angle for the closest stars is something like the width of a dime at a distance of 6 kilometers. It's ridiculously small. and only stars within about 300 light years could have their distance determined by parallax measurements. I think that's gone up a little bit, but in general, we've moved on to other methods of determining distance. So the closest star to us is the sun. And a star is a self-luminous sphere of hot gases that's energized by a nuclear reaction and held together by the force of gravity. The nearest star to Earth is, of course, the sun. It's the most studied star. It's how we figured out most of what we know about stars. And the sun is enormous relative to the size of it. It's about 100 times the diameter of Earth. It's really freaking big. Yeah. So here's a short video about the sun.
While billions of stars are scattered throughout the universe, the one at the center of our solar system plays a special role for us here on Earth. Our sun formed about 4.5 billion years ago in the Milky Way galaxy's Orion spur. It was born when a cloud of dust and gas, known as a solar nebula, collapsed. And in the middle of this formation, matter condensed into a burning ball of gas that became our sun. The sun's fiery nature, along with a tremendous gravitational pull and an extensive magnetic field, helped it to become the heart of our solar system. The sun can be divided into 6 layers or regions: the corona, the chromosphere, the photosphere, the convective and radiative zones, and the core. In terms of atom count, the sun is about 91% hydrogen, the sun's fuel, 8.9% helium, and 0.1% heavier elements, such as carbon and nitrogen. Due to the sun's extreme temperatures, these elements stay in a gas-like phase called plasma. In the core, temperatures reaching at least 27 million degrees Fahrenheit, combined with the sun's powerful gravity, fuse together hydrogen molecules to create helium. Called thermonuclear fusion, this releases an enormous amount of energy in the form of radiation, electricity, solar wind, and, as we experience on Earth, life-giving heat and light. Such volatility is contained thanks to the sun's tremendous gravity. It's strong enough to hold the solar system intact and is primarily due to the sun's size and mass. Our sun is the largest and most massive object in the solar system. It's more than 100 Earths wide and could theoretically fit all 8 planets inside nearly 600 times. It also contains approximately 99.8% of all the mass in the solar system. Because of this mass, the sun has a great pull on the fabric of space, creating a gravitational force that causes nearby planetary bodies to be drawn toward it. This gravitational pull allows the sun to hold together a system of 8 planets, potentially dozens of dwarf planets, at least 170 moons, and countless comets and asteroids. Without the sun's gravity, these celestial bodies would drift off into deep space. Another critical property of the sun is its magnetic field, which encapsulates the entire solar system. Called the heliosphere, this force field protects the planets from harmful cosmic radiation. It's caused by the sun's plasma pushing electrically charged particles toward the star's poles. This process turns the sun into a giant magnet. Although the sun's magnetic field is invisible to the naked eye, its effects are noticeable. On the sun's surface are dark areas called sunspots, which mark strong pockets of magnetism. On Earth and on some of the other planets, the sun's magnetic field interacts with their atmospheres, resulting in beautiful auroras. Despite its size and strength, the sun will not last forever. In about 6.5 billion years, it will run out of its hydrogen fuel, expand to envelop Mercury, Venus, and even Earth, and then collapse into a small star known as a white dwarf. In the meantime, the sun will continue to play a critical role in the system that bears its name. The sun's protective magnetic field, tremendous gravitational pull, and ability to create vast amounts of energy will protect, contain, and give life to our solar system.
Okay, so we'll stop there for today. Just a reminder, we have a lab today, so make sure you